Okay, so we've been looking at how we can approximate function values with Taylor polynomials, but an approximation isn't worth very much unless you have a way to determine how large the error can be. Okay, so in this video we're going to look at a result that gives us a bound on our error when approximating a function with one of its Taylor polynomials. Okay, this is what's known as Taylor's remainder theorem. So first off, we're going to call the difference between f of x and Pn of x the Taylor remainder, or just the remainder, and we'll denote it as Rn of x. And what Taylor's remainder theorem says that when approximating f of x by Pn of x on a closed interval, which we'll denote by I, this remainder can be no larger than this following quantity. Okay, it can be no larger than this number m, which I'll say more about here in a second, divided by n plus 1 factorial times x minus a in absolute value raised to the n plus first power. Okay, so again, the quantity you see on the left of this inequality is the remainder term. Okay, now what is this number m that you see on the right? Well, m is an upper bound on the n plus first derivative of f in absolute value on the interval I. Okay, so in other words, the n plus first derivative in absolute value can be no larger than this number m for all x in the interval I. Okay, so how do I go about finding this upper bound on the right-hand side? Well, it's really a two-step process. And let's illustrate that process with this example. So we have f of x, which is e to the x, which you've seen now quite a few times. And our base point a is 0. And here we'll look at this function on the interval I, which is the closed interval from -1 to 1. Okay, and let's say I want to approximate e to the x with p4. Okay, and then we found pn in a previous video. So p4 here is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. I'm going to bring up a graph just to help us visualize what it is we're doing. So here is e to the x on the interval from -1 to 1. And here is p4. Now if I graph p4, right, that's in red, I can see that at least from this view, it looks like it just perfectly overlays the blue exponential curve, right? If there is error, it appears that that error is rather small. Okay, our goal is to get an upper bound on the error if I want to approximate f of x with p4 of x, and that bound is going to hold for all values of x on this interval from -1 to 1. Okay, now notice if I zoom in towards one of the endpoints, okay, I do start to see that there is some gap, right? So there is error. Now if you go close to the base point, okay, things are really, really close. Okay, you can hardly see any gap. It's at those endpoints where it looks like we're getting some gap. And our job, again, is to find an upper bound on that gap, right? So there's really, again, a two-step process in doing this. Okay, our first job, we're going to find this number m. And then the second job is to find the maximum value of this quantity, which is this x minus a in absolute value to the n plus first power on the interval I. Okay, so let's go ahead and start by finding m. Now here, since we're using p4 to approximate our function, n is 4. And so the n plus first derivative of f here is the fifth derivative, right? And what's the fifth derivative of e to the x? Well, that's just e to the x itself. And so what we're really asking here when finding m is how big can e to the x, which is the fifth derivative, in absolute value be on this interval I, which is from -1 to 1. Well, here's a graph of e to the x on this interval. And what's the largest this function can be on this interval? Well, from the graph, we can see it takes on its maximum value at this right endpoint, right, when x is 1. And so we conclude here that m is equal to e to the first power, just plugging in 1 in for x into the fifth derivative. Okay, so m then is equal to e. All right, so that's step one. We got our m value, and now what we're going to do is find this maximum value of x minus a in absolute value to the n plus first power on our interval. Okay, so note a is 0, right? So x minus a is really just x. And again, n is 4, so n plus 1 is 5, right? So we're really looking at x in absolute value raised to the fifth power, and we're asking how large can this quantity be on this interval I, which is from -1 to 1. Well, x, right, can be no larger than 1, right? So this quantity will be bounded above by 1 raised to the fifth power, which is, of course, just 1. Okay, so we've now put that all together, okay? R4, the remainder when using P4 to approximate our function e to the x, can be no larger than m, which we found over here is e, divided by n plus 1 factorial, so that's 5 factorial, times x minus a in absolute value raised to the n plus first power. So that's just x in absolute value raised to the fifth power. And then from this second step there, we found, right, that quantity, x in absolute value raised to the fifth power, can be no larger than 1. And so we're saying that our remainder, in fact, is bounded above by this number, e over 5 factorial. So, in conclusion, we see that the error in this approximation is bounded above by the number e over 5 factorial, which is about 0.02265. Okay, so again, going back to this picture, what Taylor's remainder theorem guarantees is that if I use P4 of x to approximate f of x, my error can be no larger than about 0.02. Okay, now of course the error might be less than that, and if I'm really close to the base point, right, we're almost certain that the error is less than that number. But the point here is that that bound works for all values of x on this entire interval. Okay, well that's going to do it for this problem. Now in the next video, I'll go through one more example illustrating how Taylor's remainder theorem works. All right, thanks so much.